This week we're going to continue with integration and learn a few more techniques. Last time we looked at integration by parts and trigonometric integrals. The next topic is trigonometric substitution. Now there are a few identities. Basically, there's one major identity which helps us solve some integrals using trigonometric substitution. It's based on this identity, which is that 1 minus sine squared equals cosine squared, or equally well that 1 minus cosine squared equals sine squared. What it basically tells us is that I can replace 1 minus something squared by a single squared quantity. Similarly, I can derive the other identity from this by dividing everything by cosine squared to get tangent squared equals secant squared minus 1. So this gives us a certain strategy for solving integrals. For example, if the expression is a squared minus x squared in the square root, the substitution x equals a sine theta would help us solve, because I would end up with a squared. If I do the substitution that I just claimed, I would end up with a squared minus a squared sine squared theta in the root, which is a squared 1 minus sine squared theta, which is a squared cosine squared theta, which is a cosine theta. So basically I get rid of the square root if I do that. Similarly, a squared plus x squared, the substitution of a tangent theta works because 1 plus tan squared theta is secant squared. And x squared minus a squared, a substitution of a secant theta works because secant squared theta minus 1 is tan squared theta. So the objective is to get rid of the square root. Let's look at an example. Square root of 9 minus x squared over x squared dx, because this is of the form a squared minus x squared. So this is 3 squared minus x squared, right? So a is 3. I can use x equals 3 sine theta. If x is 3 sine theta, dx is 3 cosine theta d theta. Making the substitution, I end up with cotangent squared theta. But then I can write cotangent squared theta as cosecant squared minus 1. And the integration of, so this is because integration of cosecant squared theta is negative cotangent theta minus theta plus c. But we're not done yet because we had made a substitution. And the substitution was that x equals 3 sine theta, right? So if x over 3 equals sine theta, then theta equals arc sine x over 3. So you can write the result as negative cotangent of arc sine x over 3 minus arc sine x over 3 plus c. But also you can make it much nicer, because sine theta is x over 3. That means it's the sides of a triangle with angle theta, where the sides are opposite and hypotenuse. So you can find the adjacent as square root of 9 minus x squared. So that cotangent now becomes opposite of tangent, which is adjacent over opposite. So square root of 9 minus x squared over x. So your final result in terms of x can also be this expression, negative square root of 9 minus x squared over x minus arc sine x over 3 plus c. Now here's an interesting application of this. We can use this method of integration to find the area of a circle of radius r. You always learned that the area of a circle is given by pi r squared, and now you have a method by which you can actually find it. And instead of using the whole circle, I'm going to use a quarter circle. And the equation of a circle is given by x squared plus y squared equals r squared, where r is the radius. Which means the equation of this particular part over here is given by r equals square root of, y equals square root of r squared minus x squared. For now, we're going to say that area is the integration, or integration gives us the area, and the quarter circle is going to be 0 to r of square root of r squared minus x squared. So we do our standard substitution, x equals r sine theta, dx is r cosine theta, which means we have this triangle with angle theta, where sine theta, which is opposite over hypotenuse, is x over r. So giving me my adjacent as root this term. because I made a substitution, when x is 0, theta is 0, and when x is r, theta is pi over 2. So I end up with this expression. Now over here, you can either use a reduction formula for cos squared, or you can remember this identity. Cosine squared theta is cosine 2 theta plus 1 over 2. And you end up with a linear term of cosine. Okay, leave the r squared outside. You have a 1/2 integral of sine theta over 2 from 0 to pi over 2 is 0. And you end up with pi r squared over 4. Now that's the area of the quarter of a circle. There are 4 quarters in a full circle, so the full area is pi r squared as expected. This next example here highlights another trick that you may have to use sometimes. That is completion of square. Okay. On first notice, this doesn't look like something where you can use the strategy we just learned, because it's not in the form of a squared minus x squared. But you can rewrite 3 minus 2x minus x squared as 4 minus 2x minus x squared minus 1. And then that becomes, maybe let's write another step here, 4 minus x squared plus 2x plus 1. And this x squared plus 2x plus 1 is nothing but x plus 1 whole squared. So I can rewrite this entire thing as 2 squared minus x plus 1 squared. So I do 2 levels of substitution. First, I make u as x plus 1. And I end up with 2 squared minus u squared. And then I let u equals 2 sine theta, giving me this triangle. I'm going to let you work through this yourself, and you should end up with this expression, which you then need to convert to u, which you then need to convert to x. Another example is an example with tangent here, because this is of the form a squared plus x squared, right? Where a equals something that I need to find in this case. Kind of like a squared plus x squared, which means it's tangent, etc. But it's not really x squared, it's 4x squared. So what I'm going to do is I'm going to divide everything by 4. And, or equally well, I'm going to factor out 4 to make it x squared plus a squared, right? So it becomes x squared plus 3 over 2 squared. You let x equals 3 over 2 tangent theta, so on and so forth. Make sure you change the limits. You go through the calculation, substitute theta. Once you're here, you substitute e equals cosine theta, and you should get 3 over 32. So all the steps are written here. I'm not missing any step. I will advise you to go through this problem yourself so that you know what to expect when there is a tangent theta substitution, because all of these are strategies for solving, which means they follow pretty much the same pathway. That's it for this video. We're going to learn another technique in the next video.